All right, good morning. Welcome back. I hope you've enjoyed your first day and a half so far. Again, we're really so happy that you could be here with us. We're going to kind of continue with what we talked about yesterday a little bit, and then we're going to get into convolutional neural networks. We actually see a version of a convolutional neural network right here. And so this is a little quadcopter drone, and this is going to have an onboard camera and an onboard computer. And it's going to take the picture of the trail, and it has to choose an action. It has to choose, am I going to scoot right? Am I going to scoot left? Am I going to just go forward down the trail? And so it has to somehow reduce this camera image, which might be millions of pixels if you put a cell phone on here. You want to reduce this down to 3 numbers. We have to go from millions of numbers down to 3 numbers. So we're going to look at how that happens. And let's jump back a little bit and look at the MNIST that you were working with yesterday in the Jupyter Notebook. And so MNIST is this collection of handwritten digits. And how did we learn how to recognize handwriting? Well, in school, right? You went through years of first and second grade kind of thing, kindergarten, learning how to recognize these digits. And so what a convolutional layer does is you're going to take your input and you're going to apply a bunch of different filters to it. Oh, great.
It wasn't.
Yeah.
Is this something that the network itself does, or is this something that we pre-process before going into the network?
So this is the only thing that goes into the network, and the network is going to figure everything else out. Let's see, did it show up on here? Do we need
Back there, is that?
Yeah, 1 second.
Okay, we don't need that one. Okay, awesome. So what we're going to do is we're going to take this image, this input of this pixels of this 8 here, and we're going to apply filters to it. Now we're all familiar with filters because this is what's on our telephone. When you pull up the camera, it shows you what you look like, and then it has all these options that you can filter your image with. You can make it grayscale, you can make it sepia, you can invert it, you can flip it upside down. That's what these convolutional layers are going to do. They're going to take our image and they're going to apply different filters to that image to try to create different copies. The idea is I want to figure out, is this an 8, is this a 7, is this a 5? It's certainly not going to make it worse. What we do is we're going to take that one image and turn it into 6 images, each a slightly different version of the original, and then we're going to send that through to the network. So instead of giving it 1 photograph to consider, we're going to give it 6 photographs to consider. And then what we do is we're trying to throw away numbers, right? This MNIST is 700 and some numbers. We need to go down to a number like 1 to 10. We need to know what the digit is. So we have to start shrinking things. And so one of the ways to do this is to pool the pixels. So pooling just means you're going to look at 4 pixels at a time, and you're going to find the brightest one of those 4, and you're going to replace it with just 1 pixel. So you're throwing away 75% of the numbers. Just a way to sort of throw away numbers. So in this process, we're going to have to start shrinking and shrinking. So that's what we've done here. We've taken, this is the original, we can take it and make 6 copies, and then we're going to downsample. You can think of just skipping pixels almost, right? So we can, there's different ways we can do that. We can do max pooling, which will take the largest of an area and replace it, or we could take the average of an area. But in reality, all we're trying to do is we're trying to shrink that image. Then what we're going to do is we're going to do the same thing again. We're going to take each of these and we're going to make copies of it. So we're going to try to find slightly different versions. And after you get past these first layers, these features get very abstract. It's hard for us to interpret them because our brain is made to look at this layer of stuff. So these quite don't make much sense to us anymore. But what it's trying to do is sort of look for features, and then it's going to pull that down again. So these shrunk again. So now we have tiny images. And so now we're going to feed those this whole stack. You think it was like almost like a movie, right? These are all the different frames. We started with 1 frame. We went up to 6 frames, and then we've gone up to even more now. And so now we have all these little mini frames. And then from there, we're going to send this to a network. So we're going to look at the weight. We're going to weight each of these pixels here. Is going to get a number associated with it. And then with the final layer, we should get one little, this grandmother cell kind of idea, that we're going to get one little neuron that lights up that says this is an 8. And so if we look at what this looks like, here we have a 2 up here. It's very blocky and pixelated. And we're going to take each of the pixels and sort of put them one at a time over here. And we've sort of taken our image and we've stretched it out into a list of numbers. Think of like one column in Excel of 784 numbers that represents that. It's the brightness of the pixels in that image. We can tell immediately that's a 2, but that's what we want our system to be able to do. And so what each node is going to look for, it's going to look for a pattern in the previous layer. So each node here is connected to all of the other. You see there's a lot of edges and connections here. Each one of these gray wires is a number that you're going to have to tune in your network. So when this thing starts out, these are random, but through the process of gradient descent, all of these gray wires are going to adjust themselves such that these are looking for appropriate patterns in the previous layer. These will look of patterns of the patterns. And then finally, from the pattern of the patterns, we'll be able to decide that that's a 2. So we have the brightness of each square is a number. That's going to tell us sort of the activation. This is sort of like the retina. This is the very beginning. We have a 28 by 28, so it's going to give us 784 of these inputs. Each one of these will now be an input to our neural network, each pixel. And then we want our network to be able to deal with the different brightnesses and try to understand what these mean. If I were to just print out this list of numbers, you'd have no idea what it was. So as we train this, we're going to give it the character in addition to the category. So we know what the actual number should be. So we take the input, we bubble it through, and when it first starts, it's going to be wrong. It's going to be very wrong because these things are all random. So it's essentially just guessing. But we can give it 1. We can say this is a 4. Let's see what it looks like. And in this process of going forward and backwards, you have the forward pass, which gives you a guess. You then get an answer key, just like you're going to take a test in school. You then get an answer key, which gives you a score, tells you how many of these you got wrong. And then from the error, you can bubble back, and the gradient descent will tell you how to change these connections here based on how wrong you were on your test. So say you take a standardized test, you fill out all the bubbles, you turn it into Scantron, you're going to get back, it's going to have a score at the top. That score is going to tell you how much you need to study. Right? If you ace the test, you get 100, you're good, right? Go to the beach. If you get a very low score, you're going to have to change a lot of your neural networks. You're going to change your behavior such that you adjust these weights. And so we can do this directly mathematically with this idea of back propagation. So in the mid-'80s, there was an algorithm developed by Jeff Hinton called back propagation, and that allows us to tune the weights of these networks. Given an input here, we're trying to break it up into features. Each of these is going to be a feature. Maybe you can see here just as an analogy, it's going to kind of look for little line segments at different angles. And then this one's going to look for combinations of those, maybe like a tail and a circle. And then from there, we could say, oh, 9 has the combinations of circles and tails. That's what 9s have. And so we're breaking this down into different features such that at the end, we have a sort of a disambiguated set of features, like if we have the hook and the tail. So back propagation is the recipe. It's the computer algorithm that tells us how to tune these weights. The breakthrough in deep learning is the ability to tune those automatically for any network you can imagine. The recipe that was developed in the 80s only worked for 1 or maybe 2 layers. But you couldn't make arbitrarily complex networks. There was no recipe about how to tune the weights. Some of the networks now, it's not uncommon for them to have more than 150 layers. You don't need 150 layers, yeah.
Do you know in advance what the layers are doing? Or will simply emerge?
No, they'll simply emerge. I mean, it's an interesting question, like can you constrain some of those layers if you wanted them to do something? But in general, these are going to sort of decide for themselves what they represent. So here in an analogy, this one's sort of looking for different pieces, and then this sort of combinations of those pieces. But that's going to be free for it to choose. And so if you give it face data, the features that will be eye-like features and nose-like features. If you give it MRI images, it'll be brain-like features. If you give it automobiles, it'll end up, putting wheels and hubcaps and stuff in there.
Let me see if I got it straight. You mean that, or I interpret that by the process of back propagation, the signal activates one perceptron or does not activate it.
Say again, I'm sorry?
Let's say we got the output of a convolution network, and then it goes propagated, the signal is going propagated to the one of the layers.
Yeah, so
the way that the resulting weight activates that perceptron or does not activate it.
Yeah, so say it's activating this 9 here, right? And so since it's actually a 9, we don't need to adjust the weights. But say it said it was a 7.
Mm-hmm.
From that, this automatic differentiation will give us an explicit recipe of how to change every single line in here, such that next time it's more likely that it will choose a 9 for that one. It won't work perfect. You know, you're sort of nudging this thing in a direction each time you make the pass, and it's sort of like a moth. You know, it doesn't actually go in a perfect straight line. It sort of bounces all around, because you know, you think about, well, why can't we just actually get the direction, right? There should be an exact amount we should tune each knob each time. Well, that depends on the image, right? It depends on the actual 9 that we gave it. So in the case of cats and dogs, you know, sort of the error surface here is defined in terms of the space of all possible cat and dog photos, which we don't really have. So we kind of approximate this by using a batch. So we take a small little chunk of data, and this will give us a general direction of how to update the parameters, and then we're going to loop that. Right, and so it's kind of like playing mini golf. We're going to take lots of little putts so that we get, and we'll see the learning rate in just a minute. Yeah.
So how did we used to do OCR when we didn't have neural networks yet?
It's a great question. I actually came across, there's a documentary I can send to you about OCR, you know, going back decades, and it's not neural networks. They had a system that would try to find, it would like scan across until it found like the leftmost region, and then it would like scan up, and so it looked for features. It's very similar. In some, you know, it's analogous, but it wasn't quite a neural network. But it did try to find like the lower left thing, and then it tried to trace up some lines and see where some features are. And it worked, but it only worked for specific fonts. And so they had computer machinery that could read, like, you know, the postage, automatically read the address if you typed it in a particular font. And they had that in like the 60s. Yeah.
Well, we sold the Kurzweil system that you trade. The thing would do, you'd scan the text, and it would take its best shot at it, and it would highlight the letters that it didn't understand and ask you what they were. And you would train the machine over, you know, 8 or 10 pages, and then, you know, you had a legal document, you had, you know, 300 or 400 pages in this thing, and it would get up to about 96%. But the problem, there was another problem, because it would incorrectly recognize a letter and not realize that it made a mistake.
Yeah.
So
4% of your characters are wrong.
But, we had a customer that did a case, the Hitachi suit out in California. They had, I think they had something like 20,000 pages to convert, and they never got it beyond 95%, but it was accepted.
Right.
As,
It's probably good enough. Then if you run a spell check over it, it can probably fix most of those. Yeah.
So was this considered AI or machine learning?
The OCR I was just telling you about, I would say it was really neither. I would say that was hand designed. That was sort of hand engineered. Given a particular font, how can they sort of scan around to disambiguate each letter? They positioned the letters in certain ways. There's actually magnetic versions too. There's some magnetic ink. In some systems, they could print magnetic ink, and the characters are really kind of funny, right? You see them sometimes on checks still, where like the A will have like this big blobby thing on one side, and they sort of have like these weird blobs on it, and that's to make the characters more distinguishable. And so, say you train one of these, like the Kurzweil system, and it gets 96%. If you change the font or even the font size, you know, it would probably fail miserably. So the cool thing about these is they could handle like arbitrary handwriting. I did come across one that they implemented in the 80s to read the serial number off of microfilms. And so it's like you have these libraries with, you know, shelves and shelves of microfilms. You want to catalog them automatically. You don't want to, like, you know, type that number in. So it's like a very unique font. And the neural network was able to learn that particular font and then, you know, scan those in automatically. This convolutional system that we're going to show in the next slide or so, Jan LeCun, this has been around since like the mid-90s, and it processed a significant number of the checks in this country in the 90s. So this idea, we want to go downhill, right? We don't know how to adjust these wires. And unfortunately, when we have this many wires, it's impossible really to visualize this geometrically. And this isn't a particularly elaborate network at this point. This is what we would call, you know, like sort of a, depends on how you count. Some people count, you can count these as the layers, right? And we could say this is a 4-layer neural network. Or the really interesting thing is the weights. We could say there's 3 sets of weights here. Imagine we had just 2, right? So if we look at just this top wire and that top wire, we have 2 numbers that we need to adjust. Assume all the rest are already perfect. We sort of had some magical genie oracle comes in, sets all of them except for the first 2. And now we have to figure out, all right, how do I adjust those first 2 numbers? So what we want to do is we want to create an error landscape. We want to measure how wrong you are. And so imagine you've taken your test, you've taken your Scantron test, and you're going to get a number. You're going to get like, did you get 25 points wrong? Did you get, how many dogs and cats did you misclassify? you're going to be given 100 photographs of cats and dogs. If you're just guessing at chance, you'll get a 50%. If you know what cats and dogs look like, you'll get none wrong. And if you're learning, you're going to be somewhere in the middle of this surface, and you're going to be trying to go downhill. So this is really interesting that we can take it's almost too good to be true that we can take an extraordinary large amount of problems and turn them into this search in parameter space. And as long as we can find our minimum here, then we have an optimal solution. We have the sort of the cheapest solution, or the ones that performs the best. And so we want to sort of go downhill. And with two, if we had just one knob here, I get sort of one thing that I could change the one strength of the top wire, and then I have another sort of adjuster that I can adjust the strength of the second wire. And if I only have two, then we can plot this as a surface. So we have how wrong you are as a function of what your settings are. So in this case, 0, 0 happens to be the best settings for the first two wires in this example, but it might not be there. This local minima might be somewhere else, and this thing might have a really funny shape. So say if we were looking at this regression example again, we have some set of points. If we fix the intercept and we have just one number that we're trying to optimize, we're going to want to find the least squares of this. So in that visualization we saw yesterday, we had those blue squares, and it was adding up the sum of that, and we had how wrong the error was. So in this, we're trying to do the gradient descent here. And so here B is fixed. So we're not changing the intercept. So this is a y equals mx plus b type thing. And we're changing the slope, m. And so this is our parameter. It's not a neural network, but it's a very simple model. And then we can use this as a decision or a regression. And we want to know what's the number there. So we can see in this thing is sort of moving along, right? We can't see the surface anymore, but this is moving in the positive direction for the slope. And so it starts out much lower, and then it sort of just climbs up, and it says, I like this 1.45, 1.46. This is a good number. So when we do that, we think of maxima and minima. We're trying to find the bottom of this sort of, you can think of like a skate park or something like this. And we want to sort of find the global minima. We don't want a local minima. We want to find the best solution. So 10 years ago, everyone talked about, well, what happens if you get stuck here, right? Because in 2 dimensions, you can easily sort of imagine you're a marble, right? And you're a marble and you live in this one-dimensional world, and then you get placed right here, and you're going to go boom, 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 and you're going to get stuck there, right? But that's not the best solution. You can get cheaper than that, right? You can get a better solution, right? Think of this as like sort of, patients misclassified, right? You want to, misclassify as few patients as possible. So if we think about what this means we got sort of unlucky twice. That had this thing peeled down, that would have been better because we could have just rolled off the hill. But because it rolls up that way and up this way, we're sort of twice unlucky, right? Because it goes up in both directions. If we're in 2 dimensions, we're unlucky 4 times because this goes up, that goes up, it goes up out of the board, and it goes up into the board. So one of those could have peeled down, but if we're really unlucky, all 4 go up, and we're sort of stuck there. Really interesting and exciting thing that's happened sort of experimentally that no one really expected over the last few years is that when we get to higher and higher dimensions, what's the chance that you're going to be double unlucky in every dimension? It gets low. It gets much lower. And so the chances that one of these sides will happen to spill off and peel down the other side, and you can get out that way. So there'll be sort of a direction that you can move out and go downhill, right? So imagine you're in sort of like this big, sort of ski thing, and you can't get out, but there's like one little mountain pass that'll take you out of this thing if you go the right direction. So here we can kind of visualize that. We can start 2 candidate solutions. We can start this one. They're both just going to start randomly. By chance, one of them happens to do better than the other. This one is really getting things wrong. And then what we want to do is we want to go downhill. So we can see this one gets stuck in a local minima, where this one happened to start in a better spot and just kind of got lucky and fell downhill. So this is this gradient descent, right? This comes from physics, right? This is a theory of how planets go around and the orbits and stuff like that, that we have this dynamical system that's going to move over time. And so amazingly, we can use this framework to solve all of these neural network problems are solved in this fashion. We can't picture it, unfortunately, because there's more than 2 settings here. We just have 2 free parameters, 2 choices, and it's telling us how wrong our network is for each of combination, right? So for every combination of these 2 choices, we have a brightness of this hill. In the real world, in real neural networks, you can't try every combo, right? Here, there's only 2 dimensions, so we can just brute force it. We could say, all right, try -3 and -3, try -3 and -2, try -3 and -1. And you can march through and go for every grid point. We can run our network for those possible settings, and we can say, how wrong were you? How well did you do for those settings? And so if we map that out and we only have 2 possible settings, then we can make a whole picture, this energy landscape, where we can see instantly as a human. You can be like, we'll just go right there. But in general, you can't actually have this surface. It would be too expensive to calculate. You have too many dimensions, and you can't just go to every possible weight setting. You know, there's just too many. It's like the punch card thing. We wouldn't get through them all. So one of the things you want to do is you want to add something called momentum, right? And so moths, we're talking about moths at the light. What they don't have is they don't have momentum. They change their idea every second. They're like, I'm going to go this way. No, I'm going to go this way. Now I'm going to go this way. Now I'm going to go that way. Right? It's not a really good strategy. What it is they're trying to fix on the moon. From an evolutionary point of view, they're not used to your street lamp. That kind of just showed up overnight. So they've evolved to deal with the moon. As the moth moves around, the moon does not move. But as they move around your street light, they're like, oh, the moon is moving. So they're constantly changing the direction. You want to avoid the same kind of thing here. You don't want this to be too spazzy. So you can add this momentum step, which says take the gradient and go in the direction that your latest quiz, right? Say you bombed a quiz, right? That's just one quiz, right? It's not gonna change your whole educational experience. It was just one quiz. You need to go study. So you're gonna have this gradient of how you're gonna change your weights, but you also have these other goals, right? You had something, your whole educational path was going on a different trajectory. Just because you bombed this one quiz and this weird elective, like, who cares, right? You're moving that way. And then there's sort of fancier ways to do this, so you can look into this kind of stuff. So here's a half a dozen different techniques for sort of going downhill. So this is our stochastic gradient descent. Here's momentum. And some of these other ones, RMS prop, add a grad, add a delta. You can sort of look these things up if you're so inclined. But what's really cool is these are all sort of available in TensorFlow. And so you can just say, I want this one or that one. Right now, you can just, the vanilla version is all we really need to worry about, is that this thing's going to kind of go downhill. But if you see the red one, it kind of sticks there for a while. It's not really nearly as efficient as this, right? So these others have sort of found this other mountain pass out, whereas the red one kind of gets stuck there.
I have a question.
Yeah.
What are each of these responses when they hit the valley? And does the momentum one go much further than, say, the other ones? And do some of them have really good approaching skills and really bad stopping skills?
Yeah, it's a great question. I think there's so much area, because you get these like video game characters. You can make up all sorts of like properties they have that they like to speed up and then slow down. And when they find something, they do this. You can have them even communicate with each other. So something I did some years ago was particle swarms. You can actually have these different solutions now talk to each other, right? Who's ever fed seagulls or made the mistake of feeding seagulls at the beach? Right, what happens? Oh, like every seagull on the eastern seaboard comes to get your French fries. Like, how did they know, right? How did they know? So they have a huge geometric search space, right? The entire East Coast to search for foodstuffs. It's sort of like this landscape, like here, right? This is like the ocean, nothing to eat, and this is like your French fries. They want to be there, and so somehow they're working together. They squawk and flap and do something maybe that we don't understand, and then they're communicating together. So I think that's the really exciting thing. And then there's the idea of genetic algorithms, right? Can we take this solution and mix it with that solution, right? Take half of this one and swap it with that, and try that. And so there's a lot of whole area of research that you can go into just this optimization, right? Which was an existing field and sort of merged with neural networks. And so we get all these amazing tools that have been developed over the years about how to just go downhill. The mathematicians like to go downhill in weird abstract spaces. And now we can use that to go down in our energy surface. So here's another view from overhead, that here we'd have our best solution, and we would sort of want to find that. And we can imagine these all sort of start at different places. You can see the green ones like, whoa, I'll go back this way. So I think the really exciting research is mixing these things, get them to work together, run each one on a different computer, and have them talk over the network, and information sharing amongst these. So a lot of open research in that area. Who's ever played golf or mini golf, right? And so what happens when you get to the thing and you hit too hard in the putt, right? It goes past it, right? And you got to do like this, and then you go like this, and then you go past. If you have to slow down the putt so that it approaches but doesn't go past it, right? And so if these things are moving too fast, right? They'll go and they'll pass it, and they'll go, oh, it's over here, and then they'll go like this, right? And so you just constantly it's like the moth. You'll go back and forth and back and forth and back and forth, and you'll never actually get anywhere. You'll just jump back and forth. And so that's this learning rate. If you putt too hard, you're going to go right past the hole, and you have to turn around and go back again. And if you keep putting too hard, you'll never get it in the thing. So what you want to do is you want to have this learning rate, right? And if it's too low, it takes a long time to learn, right? See, this red one is kind of what we want. So if it's too high, it'll just overfit and kind of explode. And then we have these sort of different scenarios. So you want this thing to be slow, not too slow, but sort of that it can, approach the hole and not go past it. Right. And then I briefly want to mention this idea of overfitting. We're trying to build a model. And what does Occam's razor say? It says we want the simplest model that explain our data. So we have our dots here. There's a bunch of dots. And we have two proposed models to explain this sort of data, right? So this might be age versus shoe size. This is very highly correlated with kids, right? You can guess the shoe size. You can guess their shoe size from their age. Or other, you can actually guess their vocabulary from their shoe size, which is actually kind of interesting, right? Because it's not really their shoe size tells you a kid's vocabulary. It's the shoe size tells you their age, and their age will tell you their vocabulary. And so you can guess their vocabulary from their shoe size. So imagine this is something funny like that. And I want to imagine that there's a model I have of how many words kids know versus their shoe size or their age. And I could propose this blue line. I could say, well, when it's here, and we didn't actually observe anything here, but here's a function that happens to pass through every single point that we have. So there's zero error. It fits our data perfectly. Who thinks that's a reasonable model? No, it's too complicated. It's too convoluted. It's too crazy, right? So this simple model is something that we're going to prefer. And then I just want to mention the dropout. We'll talk about more about this later, but this is what Mike was briefly talking about is a really cool regularization technique that you have the neurons, sort of unreliable. And so I have sort of a story I imagine where you have a workshop. There's a bunch of breweries in town. You imagine you got this brewery, and at night you get all this mess all over the floor, the hops and stuff, and you got to sweep it up. So there's two people that sweep up the brewery every night, and one of them's Goofus and one of them's Gallant, right? So one of them, Gallant, he's going to sweep up the room every night, clean the thing up. Goofus is just going to go on his phone all night, do great. The manager comes in the morning and says, "Great job cleaning up, team." Right? They have no idea that Goofus hasn't done anything. So what you do is you rotate their schedules out, so they're not always working at the same time. So every once in a while, you get two Goofuses working, and then the manager comes in and is like, "How come nobody swept the floor?" Right? And so this is what you can do with neurons. Neurons are lazy. They're little animals. They don't, they just want to be fed. They don't even know that they're in a brain. They're just in this local ecosystem, and they're trying to get calories. And if you don't ask them to do anything, they'll die. If you ask them to do too much, they will die. And so they kind of want to do the right amount of stuff. And so you kind of, one way to incentivize them to do interesting things that are not what their neighbors are doing is that at go time, you turn off neighbors randomly. So each neuron will only participate in any given forward and backwards pass with some probability, right? So with some probability, say 50% or 10%, the neuron will just stay home that day. So I'm not even listening to my neighbors, and I'm not going to talk to anybody. And it just drops out of the network. And by doing this, you can break up these clusters where you have one neuron that was doing all the heavy lifting and another neuron that was just sort of sitting there eating your blood sugar. So this is what you kind of want. And so this dropout was a pretty big deal. Just came out a few years ago. So we talked about the whitening data, so I'm going to skip that. Now let me switch over to our convolution now. And we're going to talk about how do we get this to really scale up to images. Because with the MNIST, we had 784 pixels. We can tie a wire, a neuron, to each of those pixels. But now we have a 4K image. That's a lot of neurons to have, a lot of weights, a lot of synapses. So we want to reduce that. And so convolution is something that can do that. And it allows us to do really cool things like labeling scenes. So this is really cool where you want to have, this is like a 360 camera just driving through the world. And you want this to label all the regions. You want to say, this is car, this is road, this is person. Right? How do we do stuff like that? And so we had to take in a huge scene, right? This is a lot of pixels down here. It's sort of downsampled for YouTube, but this is a lot of pixels. It's not really going to be practical to tie a weight to every single pixel independently, right? There'd be just too many. And for another reason, like with the cat example, if we slide the cat over a little bit, we wouldn't be able to recognize it at all. We'd have to see the cat in every possible location for us to learn what it is. So that doesn't seem practical. So what we can do with these networks is label whole scenes, and then we can label the objects in the scenes. And so we want something that'll handle, not just say this is a cat or dog, but tell me where is a cat, right? More spatial information. Where is the dog? Show me where the people are. And then here we can see a confidence of what these things are. So this is the kind of thing that was really impossible, 10 years ago. And now this is the kind of thing we could put on the mobile app for somebody who's visually impaired. They can help them understand the scene. I'd mentioned before, 10 years ago, if you'd asked me how you would get a computer to take in pixels like this and output English sentences, you'd be like, well, make a living simulated being that's essentially alive, and you could ask it questions. This is very much just math. You could do this in Excel. You could load this as a giant Excel column, have thousands and thousands of columns, and in the last one, you could decode this English sentence, right? So as we said, 25% of the time, people are preferring the sentence that's generated by the computer system. The craziest thing is you can run this backwards. So we'll talk more about this later in the week when we get to generative networks. We can actually run this backwards. You can give it an English sentence, and it will create a photograph that has the contents you described in the English sentence. So this is a convolutional neural network. To first approximation, when you hear deep learning, people are talking about convolutional neural networks. Right? Almost think of that as like a synonym for deep learning, right? That this is when we hear about deep learning and all that, most of the time, most people are running this type of model because most of the data is imagery, and there's just sort of all of these applications like self-driving cars and medicine that are sort of just ready to go for this kind of stuff. So where do we start? Well, we start with the neural network we're just looking at. This is if we take just this piece here, this fully connected, that's the MNIST network we were just looking at, right? With the number 9 being taken apart and sent through the layers. So we're going to start with a traditional, sort of 1980s neural network. And then we're going to add to it these filtering sections where we're going to take our input, filter it, downsample with pooling, filter, downsample, and we're going to do a number of these steps to finally get back to the regular neural network. And the idea is this taking this huge visual scene and it's broken it down into an abstract visual scene that then this thing can learn what it represents. So we have sort of two halves to these networks. The feature learning half, this was the part that was typically done by hand. Historically, people would have hand designed the features. And then later we would send it to a neural network. The breakthrough is to say, let the machine decide what numbers go in these blocks such that this thing gets sort of morphed into something that the network can tell that's a car. So here's a video of the original development of this. This is Jan LeCun. He developed this working at AT&T. This is Bell Laboratories. This is a very special purpose computer chip that they ran this on. Custom 32-bit processor, which was a really big deal at the time. And you can see that it's able to recognize fonts and handwritings arbitrary. So there's a camera. He just presented that live under the thing. And then this custom chip is running a convolutional neural network. It was many, many years before we could get this to run kind of in real time on traditional regular hardware. So this read, a significant number of the checks that passed through the financial system in the mid to late 90s. So you can see these are very, odd characters with very strange fonts. And you can imagine it's never seen a 7 or a 2 or a 6 or 4 like that. But it's able to do that job. So Jan LeCun has been working. It's interesting to note his background's in psychology, developmental psychology. And he worked at Bell Labs. And Facebook has since hired him up to lead their look how happy they are. This thing's working. They're so excited. This is a big deal. Facebook has gobbled this guy up for $1 million a year salary, right? So this is the kind of stuff, how important this is, that Facebook is willing to throw $1 million a year at one person, right? What's that? He gets paid more than that? Oh, yeah, yeah. So as Reggie's saying, there's an article that just came out this month. And nonprofits like OpenAI in California, there's people who work there who have salaries of more than $1 million. So we're going to take our image. We're going to create these feature maps. We're going to filter it with different features, right? Like in your phone, we have grayscale, sepia, stuff like that. Here, we're going to have different filters, right? They're not very interesting to look at as a human, but we're going to take it. We've taken our one image and we've turned it into 4. We then take our 4 images and we shrink them. Just like on your phone or something, you can take your image smaller. Like we saw with the Marilyn Monroe, we're just going to shrink it. And then we're going to repeat the process. We're going to do convolution again, and then shrink, and then finally send it to a neural network. And so here we think of the neural network, the older version, as the fully connected, as it's called. This is going to have the inputs here like this. You're going to weight each input, go to the middle layer, which is trying to find combinations in the first layer. This one's trying to find combinations in that layer. And this is looking to make decisions based on the combinations that are presented here. With this one, instead of that, we have actually like these volumes where we think of our image as being like a 3D object. If you have a black and white image, it's just a slice, like a piece of toast. But if you have a color image, it's red, green, and blue. right? It's like a club sandwich. You've got 3 pieces of toast. And in general, you can have like a whole loaf of bread. You can have a whole stack of these slices like a film where you have a whole bunch of frames in a volume. And so these convolutional neural networks work with these image volumes. So even if you have just one single color image, that's already a volume because it's 3 slices. So here's that, as they call it, LeNet 5 for Jan LeCun. And you can see this thing sort of running in real time here. And so it's taking in the image. It's trying to guess what the category is. There's the ground truth. And then here we can see what it's doing to that image. That it's sort of breaking it up into a few different copies. Each one represents that scene slightly different, right? Some show the dark as bright. Some show the bright as dark, right? Some show the edges. And then that gets shrunk down. So this is a smaller version of that. And then we're going to pool that. And then finally, we can sort of get these very abstract features. We can't tell what that is, but then the neural network from these can say, oh, that's a 7. So as we were looking yesterday, right, we have our input, we have our weight. It's going to get all together to the output. We're going to do the very similar thing, except we're looking at a little spatial region. So we're going to take this sort of window, and we're going to do weight sharing. So we're going to sort of make a miniature neural network that's going to slide around the image, right? This is what our eyeballs are doing. Your eyes are doing this right now. You can't really see the stuff that's out here. You only see focused in a very narrow region, and you're actually moving your eyes around, right? Crazy velocity trying to sort of scan this world. And so just like your eyes, we're going to take a miniature neural network and slide it around the photograph and sort of see what it sees. So this is a version of this from the 1980s. This is called the neocognitron. So he's going to put in, with the light pen there, he's going to put a giant 2 into this thing. So he's got a digital pen there. Right? We're all used to these now, but that was a big deal back then. And he's going to encode a 2 in this. Did I pause it? I'll still go. And then what it's going to do is it's going to try to break this down. So this is like the MNIST system, but it has hand-tuned features. But we'll get to see a little bit about like what this thing is doing in terms of how they break this down. So we're going to feed in the 2. And here there's hand-tuned features. So we have a vertical feature, we have a horizontal feature, and then we have these features at angles. And what this square is going to represent is the activity of this feature spatially. So where do we have horizontal lines, right? So if we look, where is there horizontal? Where are there pixels horizontal? Well, here, and then maybe a little bit there. So we can see there's energy here and a little bit up there. It's saying, I found that feature in this location. And then it's going to report that to the next layers that are going to try to pool that, and then ultimately you get to where this thing's going to say, I think this is a 2. So if we look, where's the vertical energy? Well, there's really only a little bit of vertical right there, and then that was showing up in that one. Right, so we see, where's the vertical here? Well, there's vertical here, 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 and here. And so if we look at the report from this, is like a specialist that reports upstream, when it's found the feature it's been told to look for. So in the modern deep learning, these things will discover themselves. But in this early version, these were sort of hand-coded. People said, all right, well, we know we want to look for lines at different angles. So we want to see how can we put that all together. So the exciting thing is then this translation. Like the cat that we saw this morning, we want to be able to move this thing around and not have this change. Right? It's still a 4, no matter where it is in that world. And we don't want to have to see every example of 4 in every possible position for us to learn it. We want to be able to learn that shape of 4, and then if I see it slid over a bit, I'd say that's the same 4 kind of thing. And so we can see even with very different shapes, we can kind of get this pattern. So this is the neocognitron from the 1980s, and these sort of things worked. They tried to commercialize these even. It's pretty neat. And here they're sort of pitching that they're like, you can buy one. So to me, it's kind of shocking why a lot of this stuff, isn't, more widely known. Maybe they're victims of their own success. Maybe they got sort of industrialized early. So when you go apply for a loan or a credit card, they're sort of infamous for not telling you why you're approved or not approved, right? It just says yes or no. The reason why is because they've been running it through neural networks, and they don't have, especially in the older neural networks, they didn't justify themselves. And so you had no explanation. Right? They couldn't tell you. They can't tell you if they wanted to. And they also didn't tell you that's what they were doing. Right? So you imagine if you're Visa and you run this system and it does really good at who to offer cards to of what type and what's fraud and all that. You're not going to tell MasterCard that you're using a neural network. So I think a lot of these things, and even more importantly, if as we said, if you put these things on a fighter jet or something like that, then it's all more reason to not sort of make it public. But you have to wonder that, you go back and you look, these technologies worked. They worked certainly in lots of different areas for a long time. It's just amazing they weren't funded, at least not publicly. So you have these RGB image. We're going to break it down into another sort of loaf. So we're taking our one image, which had 3 slices, red, green, and blue. We're then going to look for features in that image. And then each slice of this, you see it has a 96 down here. So we actually, in this next loaf, we have 96 slices. And each one of those slices is a feature. So it's a version like this. So each one, so in that case, we have 96 copies. We take this one number, and here we turn it into a few different ones. But in the other, we're going to change it into 96 different slices. Then we're going to take that. We're going to do it again. We're going to pretend like that's an image again. And it has 96 different color channels. Right? It's a hyperspectral image. They're not actually colors, but we can just imagine it that way. And then we're going to do the same thing again, except for this time we're going to go all the way to 256 different features. And so that's a free parameter. This is just a choice that you have as the architect of the neural network. Someone was asking yesterday, does it choose that automatically? No, not yet, which is why you can still get a job in this stuff. So you get to choose these things. And these are these parameters that as the neural architect, you're going to decide these. So this is a very famous one called AlexNet, which is very good. And so it's going to go to 384 slices, but they've gotten smaller. Right? So here was 224 by 224. This is only 55 by 55, and then 27 by 27, and then 13 by 13. So this is like a little blurry GIF, right? This is 13 pixels by 13 pixels, and you can think of it as animated over time if you were to sort of peel through it and do it. And then we finally get down to our regular neural network at the end, our fully connected. So what does this do? Well, we want to take in something like a picture of a dog. We want to break it down into these layers where we're going to pool it and then normalize. And then we're going to, convolve and then normalize and then convolve and normalize. And we're going to go through these sequences to try to figure out what this thing's actually doing. So we're going to do a convolution. Then we talked about ReLU. This is just going to take away the negatives. Right? So anything that's negative becomes a 0. We're going to convolve it again, throw away the negatives, make them 0. Then we're going to pool it. We can shrink it. So you can see it gets a little chunkier there. The blocks are bigger. Then we're going to repeat the process. So we sort of have this same sequence, right, like 3 times. It's not that crazy, right? You're just doing the same thing. So we're going to do convolution, ReLU, pool. So convolution is the step of taking the image and turning it to multiple copies. ReLU is the step of getting rid of the negatives, turning into 0. And pool is the step of just throwing away basically every other pixel. Go to every other pixel, take the brightest of the 2, and just keep that one. So this is a really nice visualization of this process. So this kind of goes fast. Let me kind of explain a little bit, and then we'll have him help narrate this. So here's our input image. Here we see a bunch of different convolutional versions of this image. So at the very top here, we see our stack, right? This is our ImageNet stack. So if we imagine the picture we just saw with all those blocks, we had those different layers. This is our convolution, pooling, normalize, convolution, pooling, normalize. This one's slightly different. Doesn't have the ReLU, it has normalize. And then we're going to do convolution, 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 pooling, and then fully connected. So this is just the regular MNIST network, right? So the regular base network. This shows up at sort of the end of every network. You have the traditional fully connected network. And this first sort of stack is to find the features. So the fact that this is highlighted in green is showing that we're visualizing this stack. Remember we said there was 96 slices in this one? These are the 96 slices that this dog sort of input has been turned into. So these are what the neurons are looking for, right? Saying so with optimization, we can sort of find each neuron, right? Each one of these squares corresponds to a neuron. Each pixel in each square corresponds to a synapse. So each pixel is one of our numbers that we're trying to adjust. And we have to adjust the weights for each neuron, and we happen to have 96 brain cells in this first layer of this AlexNet brain. And what we can do is we can say, show me the picture that this neuron would be really excited about. It's like its favorite thing in the world. And if it sees this thing, it just kind of goes crazy, right? Whereas if it sees something else, it'll just kind of ignore it. So this is that shape. And as we see, we're going to talk a lot more about this with unsupervised tomorrow, but we're going to see what these shapes are, and you can interpret them, right? So this idea that the neural network is a black box, I think has gone out the window, right? We can say, well, this neuron is looking for yellow and blue edges, right? This neuron looks to cyan and red edges. This neuron looks for something that's dark, bright, and then gets dark again. So these are the favorite things that this neuron will see. It'll fire, if it's something similar, it'll also fire, but not as strongly, right? And so I think now we can visualize and say, these are what these neurons, and these evolved this way. When they started out, they were pure confetti. And this is what the learning rate, our gradient descent, once it goes downhill in the error surface, what that means is that these things have chosen patterns. And by going downhill, right, these things are settling on a pattern. You could evolve them. You could genetically evolve them. You could randomly random walk and guess and check them, but it would take forever to do
How
that.
do you ensemble all that together again to?
Yeah, so let's see what this is doing. So each one of these, so those were what the neuron preferred, and so now when we take the input and we can see how is that neuron responding, these two had the edges, and so we can see these have essentially extracted the edges from this scene. And so this is a specialist that reports on vertical edges, and when it sees that, it reports to the higher layers up. Yeah.
Okay, the blanks are where the neuron didn't see anything it liked.
Yes. So these are neurons that are like, yeah, I was looking for that yellow, orange thing, and it's not in there, so I'm just going to stay quiet. And a lot of times, and so what we're going to do when it gets to the N1 layer, so the next layer is going to shrink these, and this will get a little blockier because we have to start throwing away our numbers. And then the next one after that is normalize, which is going to make these sort of the contrast, right? Make these sort of pop out. There's the pooling, and there's the normalization. So it goes really quick. Hang on, I backed up. Yeah. Pooling. So let me pause it there. So you can see, did you see they get blockier? Right? It's really hard to see because it goes really fast. Let me kind of slow motion it here. There it goes. So look at the texture here, and you'll see it gets blockier. Oh, I went too far. If this is going to get blockier, there's the pooling layer. So now the green is switched from convolution. Now we're visualizing the next layer in the network, the pooling layer, and so we can see these features have just gotten blockier. And this is just the idea that we have to start throwing away numbers, so we have to do something reasonable. And there's the normalization. So some of these that it wasn't obvious that they had sort of found something, you can sort of amplify what they did see, and then sort of get so that you get a report from everybody, kind of thing. And so we've taken this one photograph of this person and say you're Facebook and you want to know who that person is. You can either give it just this or you can give it all of these together. And so the idea is that all of this together might have, some, maybe not more information because it came from this thing, but there's something in there that might be easier to make your decision. And so now it's going to repeat that process. So it's going to go quick here, but it's going to go. So we saw those things that were sort of the favorite things, those stripes and the two different color edges. When you get to the higher levels and you ask the neuron and say, what is your favorite thing? It doesn't necessarily correspond to anything in the real world. Right? Maybe this is where artistic creativity comes from. We'll look at this more with GANs, but it's really interesting to think about what these things, like to see. It's weird. They don't correspond to object categories. Which is why you can imagine, the electrophysiologists that are taking apart real animal brains or real human brains as we were looking at, and you're in there and you're like, where's the Halle Berry one? Like, there's nothing in there that's going to correspond to even, anything like that.
So are each one of these boxes an output of each, so like the first hidden layer node is the first pixel on the top left, the second node is the second pixel, or how are these plotted?
Okay, so let me.
I'm just curious, like what the correlate. I understand that it's looking for the the lines vertically and so on and so forth, but how is it then looking at each pixel and then outputting that for this and giving you the answer in relation?
So it's sort of moving through these types of layers. So I'm not sure if I fully understand your question, but what it's doing here is it's showing each, like, so in the first one, it's showing the 96 versions of these, sort of all laid out. And then he does the ReLU, and then the pooling. Well, there's that one slightly different because it doesn't have the ReLU. He does the normalization and then the pooling in the other one.
Again, how do you ensemble all that rice with mango mixed?
With what?
Rice and mango.
Rice and mango?
And then you ensemble again to get the original.
Just the visualization part. I understand how it works, but just the visualization for us to see that picture kind of looks like that picture, but with those lines there.
Oh, these here, like this version?
So from this, then the next one. So like this is what it's looking at of how the pixels are changing across.
Right.
Then how is it sweeping across all of that and out? Is it doing this all the way across, and every time that's true, it's making a new matrix with a 1 in that?
Exactly. So okay, yeah. So you're gonna take one of these little features, and then I'm gonna take this thing and I'm gonna sweep it across that whole image. So I'm just gonna sweep this around that image. And if say it's like nothing like the thing that's underneath it, right? Like this, there's not very much of this blue-yellow kind of stuff. And so this is not really going to report. It's going to move all the way across, sort of like cookie cutter, every possible position it could be in. And then for each possible position that it could be in, it says, is the thing in the photograph in this spot like the thing that I am? How similar is the picture here to my this pattern, right? And so if there happens to be an edge there, it'll put a brightness there. So when we saw that red 2 being put in, and there was the vertical feature, in the next little square, it had the energy of where there was red where that vertical component was found. And then where the horizontal component was found, it was somewhere else. Right? Does everybody remember that picture? The sort of that red 2 and those vertical edges. And so that's what we get here when we look at this version. What we have here is this is a reporting of where these are the 2 vertical edges. This is a reporting of where the vertical edge is found. And so this is saying that I didn't find any of my feature over here. And this one, which was that blue-yellow thing, that was found nowhere.
So this isn't necessarily the output activation of that node while it's running. This is more of if you take that node and did the activation of all of this, the first pixel for this one, the second, and so on and so forth. That's what that is?
Yeah, that you're taking, we're going to have more pictures of this. So let's just keep going, then we can come back to that. So hopefully it'll make some more sense. This is really cool that once we're up into this, this 5th convolutional layer, it's now no longer sort of visual features per se. It's idea space almost, right? Or at least the edge of it. So here's this thing of a face, which is made out of the other layers. And so this neuron will put brightness wherever it sees a face-like thing. Just discovered the makeup industry. Right? Seriously, there's this neuron, and they're saying this neuron will fire even more if the image was more like this. So these are the layers in the 3rd layer that then get reported to the 4th layer such that the 5th layer can make its decision that it's found a face. So these are the things that it's building up to decide it's a face. This was the ImageNet challenge, right? This is a million images from thousands of categories or more. And he's saying that printed text was never something they asked the neural network to do. Recognizing faces and wrinkles was not something they asked the neural network to do. But they did ask it to know what bookshelves look like. And one way to recognize bookshelves is to look for printed text. So we'll send this link around. Try to get this to run, or at least, check out this video again when we send around the link, because there's a lot in this very short video. Let me go back. Deep Viz. If you type in Deep Visualization Toolbox, it'll come right up. So I'd recommend everybody going through that video again later and watching that a few times. Okay, so here's just another picture of that so we can sort of see it static. And here it's been sending a cat. And so here we have the first layer of the cat. And then, finally these things. So what we want to notice here is that these are sparse. And so we'll talk about this more when we talk about unsupervised learning. But the fact that most of these neurons don't fire to most things. For a real given image, there's only going to be a small set of neurons that are really actually going to be involved and actually have a lot of energy to the next layer. So if we look at what that looks like in terms of convolution, well, we have like a face. This is going to be made out of pixels. The pixels are going to be in numbers, right? It might be this scale, but if we blow it up, we can actually see all the values. And then like that center pixel is going to be a 191. So what is this convolution, right? So what we're going to try to do is we're going to take our kernel, which is going to be a recipe of 9 numbers. So we're going to take this little miniature neural network, we're going to slide it around our image, and for every possible spot, we're going to get a reporting, the square up there, that tells us how similar is this thing underneath to the thing that I'm sort of sliding around. So these features that we were just looking at, we're going to sort of slide them around the image, and we're going to see how much of this stuff sort of shines through, We can do this in a different way. We'll talk about more when we go to the generative networks, how we can go up if we want to make more pixels kind of thing. We'll talk about this more later. Or if, in this case, we only have a small number of pixels, we need to create pixels. So we're going to go backwards. This is something called deconvolution, or this is a bad name. It now goes by the name of convolutional transpose. And so I just wanted you to be aware that this convolution, you can go from a lot of numbers to small numbers if you want, because you have to make a decision. But in the other networks we're going to talk about later, you can have to go the other direction. You need to say, I want a cat, and it has to create millions of pixels that look like a cat. So mathematically, what this looks like is we're going to have this little kernel. There's like a little recipe, which tells us that we want to look for positive numbers here, zeros in the middle, and negatives here. You can think of this as like an edge. This is going to look for something that's bright, neutral, and then dark, right? So this is like an edge detector. And then this is a sort of a small, miniature photograph, and we're trying to figure out, sort of the feature map. So this last layer is going to be a feature map, and it's a map of how much of this feature is found in each of these possible locations that this square can fit. And so it can't fit, there's only so many places it can fit. It can fit 9 different places based on the size. And so you get this 3x3 feature map. So this is just another version of the same thing. We're going to take our feature, we're going to multiply it. So this is sort of like a weighted mask. We're going to weight everything that's underneath this particular area with this thing. We're going to multiply them. And then we're going to add that all up together. And that's our new value. Right? So we're sort of taking a weighted sum of all the neighbors. So every pixel is going to get replaced by a weighted combination of its neighbor pixels. And so we could just see what that looks like. Again, another version. The same kind of thing. In this case, we might have a color filter. And so this is kind of funny. This is actually the 3 slices. So for an image, we don't just have height and width. We have a color channel. And so the last number is telling us this would be the red channel. This would be the green, and this would be the blue. And then we're going to have a color filter. So our filter, with those filters we saw, they were in color, right? So that means they're actually a combination of red, green, and blue filters. So actually 3 filters all at once. And so we could take that and we would get a similar output. So in this case, there's going to be 2 filters. And so we're going to get 2 feature maps. So our image was a color image. It's an RGB image, so there's 3 slices. We're going to have 2 filters. Each filter has a red, green, and a blue component. And because we have 2 filters, we're going to get 2 feature maps. So there's a filter. There's our image. We're going to convolve that around the whole thing, and we're going to get a feature map. Where in this image did that object sort of shine through?
Answered my question.
Good. Awesome. Thank you. I thought it might. So you can see as we put different features through here, we're going to get different feature maps. And that's what that 96 stack was. That's that loaf of 96 that we've taken our one image and we've turned it into 96 different images. In the beginning, these will be random shapes, so we'll get sort of random maps over here. But then these will learn to be color detectors and edge detectors to sort of break the image up into a meaningful way. So here's some of these. If we and you're familiar with these from Photoshop, right? You use these all the time. So here's one that's called sharpen. And so if we add a lot to the middle pixel and then put negatives there and then zeros there, we get something like this. It just sharpens it up. If we just do an average, we put like a 1/9 in every spot, then we'll get a blur. Everything just sort of is a mixture of all its neighbors. We can do different types of blur depending on what we want to do. The identity, right? This is sort of a trivial one that we're going to just not include any of the neighbors. And just it doesn't do anything, right? You get out just what you put in. And then you can look for these edge detection. So depending on where you put the negative numbers, these will detect different edges kind of stuff. So this is what we were talking about earlier. This is the idea of pooling. It's really simple. We're going to take something that's 224 by 224 by 64, and we're going to shrink each of the slices, right? So we're going to downsample each piece of toast in our loaf of bread kind of thing so that it's a little bit blockier because we have to throw away numbers. Our camera was 10 million images. We want to know one number. Is this a cat or dog? One number. Do I slam on the brakes, right? So this is max pooling. This is our technique. There's a few different ways. We can average them, or in this case, we're going to take the largest. So we're going to go to every sub block. In this case, it's a 2x2 pooling. And we're just going to find the largest number and just replace it with that. It's really straightforward. So we're just taking the biggest pixels and letting them shown through. So as Elon was showing this morning, that this is really, I think we would argue this is the best map we have for how the visual cortex works. And, in the 50s and 60s, we found these shapes in the brain when the electrophysiologists were trying to figure out what do neurons actually like to look at, what makes them click, what makes them fire. And that's what they sort of won the Nobel Prize for finding that these things are looking for Gabors. And then amazingly, this stuff has just happened to show up in deep learning as well. Somebody was talking about the quantum computers. It was a few years ago. I was, I wanted to take a break from neuroscience, so I thought I'll do something fun and relaxing for the afternoon. I'll watch a lecture on quantum computers. So I pulled this up, and I'm about halfway through this lecture on quantum computers because this was just fun, and it shows up something like this with the Gabors, and I was just like, I thought this was the neuroscience, and it was had to do with the brain. I didn't realize it was also going to be quantum computing. So this Gabor and breaking signals down into these things is showing up sort of everywhere. We'll come back to this stuff. Let's see. All right, well, let me just mention this. Okay, so what we want to do is when we take the output of our neural network, this is going to be a vector of numbers. What we want to do is we want to turn that into a probability. And so there's a technique of doing that called the softmax. And what softmax is going to be able to do for us is to turn these things, so when we output our neural network, right, it's going to give us numbers about how much it thinks it's a dog, a cat, or a horse for these different inputs. What we want to do is we want to turn that into a probability. I want to be able to interpret this as what's the probability that this thing is a cat. And with probabilities, they have to add up to 1, right? And so this softmax is just a mathematical way of taking this output and forcing everything to add up to 1 in such a way that you can now interpret this thing as saying, okay, this is 98% sure that this is a horse. And so this is this idea of a softmax. So you'll see this in your networks now, this softmax. And then what we want to do is we want to penalize, how wrong this thing is. So this thing, it says here that this is a horse, right? And so if it's actually a horse, what we want to do is we want to say, all right, good job. Don't penalize it. So we're talking about these loss functions. And so loss functions are these things that we can add sort of your error to, and you want the loss function to be as small as possible. So what we can do is we can take this and we can look at the correct class, right? And we can try to figure out if the correct class is highlighted here in red, then if we take the minus logarithm of this. So let's go back to here. So here's the graph of the minus logarithm, right? Sounds kind of fancy, but it's just a sort of a recipe for mapping things to what we want. So what we want is when the probability of the correct answer is a 1, you did great. Don't penalize it at all, right? So if the correct answer, the correct category outputs a 1 from the softmax, that means it thinks it's a 100% probability that it's the right thing. It means it got the right answer. Then we don't want to penalize it at all. No penalty. No penalty. But if instead it thinks that the right answer, say the right answer was this one, right? Say there was actually a cat and it said 0.02. So what we can do is we can take the 0.02 and we can plug that in, and that will tell us how much to penalize the network. And so this negative log likelihood is just a recipe that you use with the softmax to figure out how do you penalize the network based on how wrong it was. So you look at the question that you know the right answer, because we're the sort of the teacher in this scenario, and so we know what the right answer is, that this one's a horse. So we look at the probability that it was a horse, and then we want the minus the log of that, which is going to give us the penalty. So this is just a way of mapping, right? When it's 1, you get no penalty, and when you're 0, that means you want to penalize this, because that means it wasn't sure. It gave a 0 probability for the right answer, which is bad. Does that make any sense? How we want to penalize this thing based on how it's wrong? So we look at the right answer, and then we can use this softmax to turn these into a probability to add up to 1. And then we use the minus log to switch that into the loss, right? How the penalty, so to speak. And so this is just an ugly way to do that, right?
Well,
Yeah.
well, doesn't it require that you have priors establish what how wrong you are translates to prior information, right?
Yeah, oh, so it'd be great. Yeah, so like if you had some other scenario, like if I know that I'm in a pasture, I should, rank this, much more likely to be a horse, that kind of thing.
Yeah.
Yeah, context. And that's what's really exciting is that this is just like getting started. When we think about like the fancy of these neural networks that we're going to talk about, this week, they might have 50, 60 million free parameters. In terms of synapses and cells, that's like a grain of rice of brain tissue. Right? Like a grain of rice. So we haven't even begun. Your question? Yeah. Okay. So we haven't even begun to figure out what does our brain do. So we might have an idea of what neurons do, and they can do all this crazy stuff, like drive cars and tell us cats from dogs and horses. But we haven't really begun to figure out, well, what's all this brain stuff? Because our DNA and our evolution has gone to a lot of trouble to make our brain a very particular shape and wired up in very particular ways. It's not just like a uniform blob of cells. And if that worked, evolution would have done that. It would have just said like DNA encode big blob of cells, be like a big sponge of nervous tissue. And then from an evolutionary point of view, that would be really easy to get to as a solution compared to all the structure and complexity that our brain has. So I think this is what's really exciting, to get into this field, is to think this is just the beginning. What we want to do is take these deep learning pieces as the Legos, and then what kind of brains or castles can we build out of these Legos that can do things that are much, much more complicated. Like think, I'm inside on the 4th floor. It's extremely unlikely I'm looking at a horse. So the neural network doesn't quite have things like that. So we want to think, how can we get multiple, maybe even hundreds of neural networks working together to solve really complicated problems like that? Yeah.
Now, what about in the case where you don't know the classification prior, and say, for example, you give it a bunch of pictures of horses and dogs, and you try to say, pull the horses together, pull the dogs together, but pull these together rather than horses?
That's what we're going to talk about tomorrow.
Oh, sorry.
You have a question in the back?
Yeah, what do you mean by, how to analyze it?
Yeah, so with these neural networks, you have this loss function, which is sort of how wrong you are in this problem. And so we think of like a Scantron test, it would be sort of how many questions you got wrong is one way to do the loss function. And so you can just count. And you can just say, you got the first one wrong, you got the second one right, you got the third one wrong, and so you can sort of just list up, and you get like a percentage score. For getting the neural network to run, it helps to do this other way of doing it with softmax. It's just a recipe.
Oh,
So if it's slightly wrong, it tells it that it's more wrong than it is, so that it changes how it weights the different values for pixels.
Yeah, that was great. You want to just say that a little louder?
It's just changing the way it weights the way that it's looking at certain pixels. So if it's perfectly right, it changes the value none at all.
Right.
But if it's completely off, it increases the amount it thinks it's off.
Right, exactly. And so this is the probability that it assigned to the correct category. And so if the thing's working correctly, it should put a 1 with the correct category. It's unlikely that it will. It sort of have some number near 1, hopefully. And then from that, we can decide how much to penalize it. So if it guesses a 1 for the right answer, then we don't want to penalize it at all. We don't want to adjust the weights. But say it outpoints a 0 for the correct category. That means it was really wrong. It was really sure about the wrong thing. And that means we want to change the network a lot. So we want to have a loss function. And so in our gradient descent, we were talking about going downhill of our landscape. That landscape is determined by how wrong you are. And so in a sense, this sort of pulls up that error landscape to make it be like, no, you're wrong. This is wrong. Right? This is not the lowest spot you can be. And so this is sort of a math way of sort of building that landscape. Any questions about that? I think this is the only equation, so I hope you enjoyed it.
In that equation, is I and j, are those the unit vector functions, or?
No, this is going to be an index, so just for the index, yeah. Yeah, it's just going to be like indexing through the loops. So that's the slides I have for convolution so far. Any questions on the stuff we covered? Do you want me to go back to any of these things and to go over again some of the pieces? Were there any questions about how some of these pieces work? Does this kind of make sense how this fits into the networks we saw yesterday? And so yesterday, or even this morning with the digits, this is what's called a fully connected neural network. And so this is the idea of a traditional neural network. In sort of the 80s and 90s, this was all it was. It was just these pieces. There's actually a theorem in mathematics that you only need this last bit, but you might have to have a lot of resources. You might have to have a really large network. So this whole bit is sort of the deep learning, the first approximation. Deep learning was stacking this bit of convolution to the neural network. And then that enables it to break the scene down into these different features. And so from these different features, we can then send that to our traditional neural network to try to make these decisions, to try to figure out which object is sort of in which part of the space.
Could you go back to the question you showed previously?
Which, yeah, tell me when. I think that was the first one. Let me go the other way. Which one?
The last one that you showed.
Oh, this here? Yeah. So this is just a recipe. So this is the softmax piece. And so this is just the way you're going to sort of normalize it. You're going to take all your values, you're going to exponentiate them. And then you're going to take the sum of that, and then you're going to normalize by the sum of that. And so this sort of inner piece is going to give you such that these values add up to 1. So in the network outputs, you're going to get something like this for each category. We wanted to interpret this as a probability. And so the softmax is a mathematical machine that will take these output vectors and make it such that it adds up to 1, and that we can interpret it as a probability. And then from there, we want to penalize that based on how, we want to give it a very large penalty if it's really unsure about the right answer. And so if there was a right answer, but it said a really low probability for the correct answer, then that means it's really wrong. So it means we want to penalize it a lot so that it changes the weights a lot, right? We have a lot of studying to do. If you get a 1 for the right, then you don't have to change your brain at all. You already works just fine. Yeah.
So in the world of doing this kind of analysis, so far everyone's been talking about categorical distinctions, but in real life, categories are fuzzy. So is that incorporated into these kinds of analyses also?
Yeah, absolutely. So yeah, we focus mostly on the classification, but oftentimes you want to have a continuous output. You're saying like a smoothly varying number?
Yeah, or a fuzzy one.
Yeah. So that's kind of what the probability can kind of help with that, and that this sort of gets a little fuzzier in that sense. But in general, we want to think of as the classification problems. We have a category and regression problems when we're trying to output like a value. So we're trying to regress to some model so that we want this to output, say, like a speed of something like that, something that would have like a continuous range. Yeah. Let's see, this one, yeah. Yeah, absolutely. So we're going to start with this image here. This is a red, green, blue. It's an RGB image. So it's actually 3 images stacked together. And then what the first layer is going to do is it's going to create a bunch of random filters. So in the AlexNet, there's 96 filters in the first layer. And what's that going to do? They're going to start randomly. And then each one is going to do this process such that you get a feature map. So from the feature and the input, we create a feature map. And that's what this is here. So this is the first feature map for the first feature. That's the second feature map for the second feature, third feature map for the third feature. So this is telling us where in this scene was the third feature present. Then the second layer, the ReLU, is the rectified linear unit. That one's going to take any value over here that's less than a 0 and replace it with a 0. So just get rid of all of the negative values. Then we're going to repeat the process. We're going to do convolution again. So we're going to take this and we're going to have a new set of filters. It's not the same filters that we had in the beginning. It's going to create a new set of filters. In the beginning, they will be random. In the beginning, they will be random. But it's going to take each one of these images. Now, this whole thing is a stack, right? So this was actually 3 images at once. And so when we had 3 images at once, our filter actually goes through all 3 color channels. It's a color filter. And so we can think of the filter as extending through the depth of the image. Let's see if there's a picture of that. This here. So we can see this goes through the feature. So this would be one sort of neuron, and it's looking at all 3 color channels. So in this next layer, we now have an image that has 96 color channels. So we're going to have a feature that is actually 96 layers deep. And so when we had our features, right, we were looking at one-dimensional features here. So here it's just 3 by 3. Imagine this is 3 by 3 by 96. So it's like a big, like sort of tube of numbers that you're taking and sort of sliding it through. And so in the first layer, it's easy to understand because it's the color image and a color feature, and we're figuring out where the activity of that color feature is in that color image. When we get to the next layer, it's now a stack of 96 slices. And so our features actually have 96 channels to them. And we're going to take that sort of, something like this, and we're going to sweep that whole thing through, and we're looking through the whole loaf at once, all 96 channels. And now we're trying to figure out where is that feature represented. And so now this is a feature map that's telling us where those features are found in that layer. Then we're going to ReLU again. So ReLU is going to get rid of the negative numbers, turn them into zeros. And then we're going to do pooling. So pooling is this one here where we just skip pixels. So we're going to take little blocks, think of like cookie cutter shapes. We're going to go to each sort of cookie, find the value that's in the smallest piece, and replace the whole thing with that. So we have, right, we've thrown away 75% of the pixels. So that's just a way of reducing the pixels. And then we're going to repeat that process. So then we're going to repeat that. So this is like sort of a chunk here, and then we're going to repeat that chunk 3 times. So we're going to
done just to reduce the amount of work required?
Say again?
Is that done just to reduce the amount of work required?
That's a good question. Yeah, could you have just like one layer and like lots more neurons? I think it's that you can get these hierarchical features, like the one that was like the face that's built out of eyes, which are built out of edges, which are built out of little lines. And so I think in the hierarchical sense, it's very powerful to have these layers. Mathematically, there is a theorem that says you only need 1 layer. But who knows how many neurons you might need in that layer. And it doesn't say anything about the complexity of training that 1 layer. It might be very complicated. Yeah.
Why ReLU as opposed to any other activation function or even no activation function at all?
It just is sort of almost an engineering thing that ReLU has shown to just train faster. There are others that you can use to have a nonlinearity there. But ReLU has just sort of become the one that's used in common in practice nowadays. It trains faster. That's right. Yes.
So what part of this data was used to get the percent change of what it thinks it actually is?
Yeah. So
just the last one?
It's just the last layer. Yeah. So this actually is a car. And so you'd look at this at the last layer, run it through softmax, and then the negative log, and that would tell you how much to penalize the network. Yeah.
Just the last.
Yeah. So in terms of what's really neat is the algorithm. Yeah, it's just going to look at the final layer. Mm-hmm. Yeah.
So if you have a scope for this method to find, say, multiple cars in a picture and detect where they are?
Oh, absolutely. Yeah. So that's like what we had, like this kind of thing. So if there was like another cat, you could have put another bounding box around the cat. And then ultimately you want something like this where you have like multi-labels where there's lots of instances of each label throughout the scene, and you want the spatial information. We don't just, so in this case, no, this is more like the generative networks, which we'll talk about on Thursday or Friday, but in general, you can imagine you want this sort of dense labeling where you might have lots of rodents. And then if you notice here, right, we're talking about like continuity and semantics and priors and stuff, it's popping up and it's saying sand here. Right? What's the likelihood of that? I mean, there could be patches of sand in the street. That happens in the city. But but that you'd want to use, maybe GPS and be like, I'm not at the beach. So this is probably not sand. And then also smoothing. You can see it's kind of jumpy from frame to frame. It's really kind of spazzy about what it thinks stuff is. You'd want to smooth that over time and be like, I thought this was road for the past 5 frames. I think it's road for the next frame. The frame I'm on, this is probably not sand. It's probably road. Okay, so I think so they're telling me we're running out of time. So we can take a few more questions. Yeah.
Would you just be able to go back to the last slide?
Yeah. So this is sort of a recipe. You can imagine in Excel, you have a first column of these inputs, which is the final layer of this neural network. Then you're just going to take the exponent. You're going to put that into the exponent, exponentiate it. And then you're going to add up that whole column. Right, and then normalize it so you can divide by the sum, and then you can just take the minus log of this. And so this is going to take our vector, turn it into probabilities, and then it's going to figure out how much to penalize this based on how wrong it was. And so that if you're correct, you get no penalty, and if you had a low probability for the correct answer, then that means you're going to get penalized heavily, which will incentivize the network to update its weights.
Can I add a little bit of smell to the Hartley-Shannon equation?
Yeah, it might be where it's from. That's interesting to think about that. All right, any other questions? All right, fantastic. So I think we're now at our lunchtime.